Yes, we can see the slide.
And okay, great, thank you. So I'll talk about temporal epidemiological model of community transmission of COVID-19 with changing dynamics, and it's the work of my students Alex Abi and Yanir Marmor, who are here in the audience with us, and our collaborator Yuval Shachar from Ben Gurion University, and I'm Ossi Mokrin, I'm from the University of Haifa in Israel. So a lot of governments debated how to enable some sort of regular life while containing the infection. Prevalent approaches were in some sort of social distancing, from lockdown to social distancing pods, with the purpose of containing the infection and ensuring there are enough hospital beds and medical assistance for those in need at any given time. In schools in Israel, the go-to solution was to separate the kids into social distancing pods, like half the kids would come on Sunday and Monday, and half the kids will come on Tuesday. And the reason they would come on alternating days was that there were not enough infrastructure to just divide them to two different schools with two different systems. So what actually became of that is that we have spatial division and temporal division. And we were interested in understanding what's the difference and what's the different effects of both the spatial division and the temporal division. Because in an ideal world, we would just divide the kids to two schools and double the amount of resources and then double the amount of teachers, and would just have smaller groups. But this was not the case, and there was a temporal effect also. So we wanted to understand that. So we look at temporal pods, in which we divide groups to disjoint subgroups without any temporal effect, just smaller subgroups, disjoints. And then we have temporal pods in which we do not restrict which nodes interact. We have the same amount of initial number of people, but we do restrict the total interactions per day. And the total interactions would actually translate to density. And density is the actual number of edges divided by the possible number of edges. And if we look at temporal networks, this would be for each window of time, what's the effective number of edges in that window divided by the possible number of edges in that window. So when we looked at that, what we found is the flow of average. And a classic example of the flow of average involves a statistician who go to swim in a river that is 30 centimeter deep on average, but rounds, right? So the falsehood of average density, we can see that on the upper panel, where we see that on the first day everybody is interacting, and then they all get sick, and then day 2 and day 3 everybody's at home. But on average, there were 5 interactions per day. So there's unbounded variance. What we would like to see is stationary density, where we bound and restrict the variance. And when we say that on average there are 5 interactions a day, this is actually the actual number, plus minus a little bit of interactions. So how do we do that? We wanted to create random temporal networks with stationary density. First, we went to Network X on Python, but it did not give us a scalable solution. So we created scalable random networks with the model from Zhang, Jiu, Moore, and Newman from 2017. And the model says that given an initial network, there is a probability of a new edge to appear and a probability of an existing edge to disappear. And together they give us the average connectivity at each window of time. And thus we created 10,000 networks with the same stationary density in each of them, with different interactions. In a network with n is equal to 1,000, so there were 1,000 nodes. And the question was, on these networks, what's the effect of separating spatial density from temporal density? So, for example, if you look on the upper panel, you see the original network with the original density that we created. When we ran an SIR model on top of that, And you can see that the vast majority of the population got infected, if not all the population got infected within several days. On the lower panel, if what you see on the left side is when we divide the groups, the network to two disjoint groups, half the size each, and then we sample. We have two initial infectors that were chosen randomly, and we can see that indeed the number of infections, the total number of infection is not as much, and we have around 70% of the population got infected, which is much better. On the lower hand side, what you see is when we divided the density, the temporal density, we halved it. So still the majority of the population is infected, but it seems that the rate is slower. So we wanted to further experiment with that on different sizes of pods and temporal density. And this is what we did. The number of splits is on the x-axis, so 1 is the original network, and then on the spatial network, the pods were divided to k, which is between 2 and 10, and on the right panel is the temporal density was halved, and then third of it, and then fourth of it, etc., etc. And we see that with two initial infectors, the results are pretty much the same. We see a vast reduction in the number of infected individuals. However, when we increase the number of initial infectors to 10, the situation drastically changes, and we see that the spatial pods do not perform as well, and between 60 to 70%, more than 60% of the population is infected, whatever number of spatial pods we take. However, in the temporal network, we see that reducing the temporal density performs best regardless of the number of initial infectors. So seeing that on temporal data, we were wondering what is the effect of manipulating the temporal density on real data. To that effect, we took a data-driven modeling, and we took the Copenhagen Networks Study data with 700 students, contact information that was recorded using Bluetooth sensor over 28 days, and we created 28 consecutive undirected weighted temporal graphs, one for each day, but with changing temporal density, we can even lengthen that or shorten that. And now we wanted to have a model that would actually enable us to predict the number of hospital beds a community of that size would require for different temporal densities. So what we did is the following. Our first assumption corresponds to the transmitted viral load. So we know that it needs to accumulate, viral load needs to accumulate in order for a person to get infected or to have the probability of being infected. So we correlated the interaction duration with the latent transmitted viral load, and following an SEIR model, what we did is we computed the daily probability of node of getting infected from its infectious neighbor by computing the probability as 1 minus the probability of not getting infected at each of the interactions. And again, the probability of getting infected in each interaction correlates with the length of the interaction. And there is a maximal probability of infection even given maximal exposure. Then, for each node, actually quite similar to the previous presentation, we created an oral disease progression model based on personal susceptibility, which correlates with age and comorbidity conditions, and we assign those to the network. So a node can be either symptomatic or asymptomatic, and if it's asymptomatic, it can have even light symptoms and then be in quarantine, or heavy symptoms and then be hospitalized, and then we can count the number of hospital beds that are needed for a population. And this is the result of the run of the simulation over the entire data set. And you can see here that the population is pretty young, majority, if you can see, the dark blue are asymptomatic. The orange colors sort of give the pre-symptomatic and mild symptoms, which are quarantined. And then in red, we see people that are with severe symptoms and are hospitalized. And we see recovered and deceased. So we can see that for the original density of the data, this was the progression of the disease in the population over the 28 days with 2 initial infectors. But we wanted to see what happens when we change and reduce the temporal density. So as you can see in the following slide, we have different runs for the different temporal densities that we have tried. And as you can see on real data in a community, when we change the temporal density while preserving the complexity of the interactions, the longevity and the number of interactions in each sort of time slot, we find that we can, in a way, control the progression of the disease in the population. So to conclude, reducing temporal density reduces community infection by lowering the meeting rates and enable the removal of symptomatic infected individuals. It slows contagion and reduces burden on the healthcare system and other scarce resources. We can even compute at the end. Big changes in the initial parameters, and this is an important result in my opinion, which is the number and location of patient 0, do not translate to big changes in the result. As for spatial density, the effect depends heavily on the number and location of patient 0. And in future work, we would like to see applications and see how we can control temporal density. And with that, I would like to thank my students Alex Abi and Yanir Momor, who are also here, and our collaborator Yuval Shachar, and I'll be happy to take your questions. Thank you.
Thank